We are starting going live.
Good afternoon. I hope you can all hear me well. My name is Chiara Benetti, and on behalf of IEA Bioenergy and ETA Florence Renewable Energies, I welcome you to today's webinar entitled Deployment of Bioenergy Combined with Carbon Capture and Storage or Utilization. The webinar will be presented by Ole Olsson, Stockholm Environment Institute, Sweden, Tero Tinjala, Lappeenranta University of Technology, Finland, Christian Bang, EA Energy Analysis, Denmark, and Daniela Tren, German Biomass Research Center, DBFZ. After these 4 presentations, there will be a Q&A session moderated by Daniela Tren and Alena Hahn from the German Biomass Research Center, DBFZ. During the webinar, from the beginning until the end, you have the possibility to drop questions by typing them in the Q&A tab that you can find at the bottom of your screen. Please use only the Q&A tab to drop questions and do not use the chat box. Otherwise, it would be a bit complicated for us to follow all the questions that you will have to ask. I would like also to remind you that the webinar will be recorded and that the link to the recording and to the presentations will be available from tomorrow on IEA Bioenergy's website. From my side, that's all. Thank you for your very, very great participation today. I'll leave the mic to Ole, and thank you for your participation and enjoy the webinar. Thank you.
Thank you, Chiara. So welcome everyone to this IEA Bioenergy Task 40 webinar on the deployment of bioenergy combined with carbon capture and sequestration or utilization. We refer to this as BECCS/U, although I have seen the term BECCS increasingly being used, and I do admit that that is more catchy, so maybe we'll switch that moving forward. As Chiara said, my name is Ole Olsson. I'm with the Stockholm Environment Institute, and together with my colleagues, I will guide you through today's webinar. Before we go into the topic of today, I would just like to say a few brief words about IEA Bioenergy. It is a technology collaboration program hosted by the International Energy Agency. And there are these TCPs, as they're called, for all kinds of topics related to energy. So there's one IEA hydrogen, there's one IEA solar. There's also one called IEA GHG, which deals with greenhouse gases, and they do a lot of interesting work on CCS in particular, if you're interested in that. It's important to note that these TCPs, they constitute a set of independent expert groups. So even though we are hosted by the IEA, we are independent experts, and we do not sort of represent the opinions of the IEA as such. And if you look at the very low end of the slide here, you'll see more of this fine print. This particular work is presented by, or has been done, I would say, within the auspices of the IEA Bioenergy Task 40, which is an expert group focused specifically on deployment of bio-based value chains. So our main focus is to try to analyze the kinds of issues that needs to be addressed to get sustainable bio-based projects up and running. So we're basically trying to tie together all the aspects of technology and policy and sustainability governance and so on, to see where where are the obstacles in sort of taking these things from a concept to reality. And today's webinar then, of course, is centered about taking BECCS, bioenergy combined with carbon capture and storage or utilization, from concept to reality. All right, so let's move to our program for today. We will basically start with walking through the whole BECCS supply chain from starting with capture in different sectors via transportation to storage. After that, we'll talk a little bit about the U part of the BECCS-U or the BECCS, which is utilization of CO2 for different purposes. We will then talk a little bit about the non-technical aspects to get BECCS projects up and running in terms of policy measures, financing, and so on. And then close the presentation with some discussion points of our own. And then hopefully you, our audience, will have some discussion points for us as well. Okay. So I guess the starting point for this whole discussion on BECCS and negative emissions is that it's becoming increasingly likely that we will need negative emissions, so in some sort, to reach the Paris targets, and especially so if we're aiming for the 1.5 degree target, which where time is really getting short. Obviously, the current COVID crisis notwithstanding, and we'll see what kind of long-term effects that will have. But in terms of the immediate emission reductions, it certainly won't be sufficient. And if we look at sort of getting these negative emission technologies up and running, ideally then we would like to get them up and running as soon as possible to sort of start sucking CO2 out of the atmosphere sooner rather than later. However, if you look at the sort of discussion on negative emissions and on BECCS and so on, it's been a lot of focus on the long-term issues and quite theoretical and based on model studies. So, and those are of course very important, but we felt there was a need to put focus on the sort of more near-term challenges and look at what are these things and how can we take these technologies or BECCS from concepts and labs and pilot plants to real world deployment at scale that actually make a difference. So just to shortly walk through the supply chain, what we're talking about, just to give everyone an overview of the terminology. A very simplified BECCS use supply chain might look something like this. So you start with some sort of biomass resource, and it can be vary widely depending on the application, of course. And then you have a process where you convert that biomass. Obviously, you do this for a purpose. It could be an industry. This could be a heat and power station or an ethanol production facility. But you're converting biomass in a way that converts the carbon in that biomass to CO2. And this could be combustion, but it could also be fermentation, for example. And then the next step is to take the CO2 once it's captured, and in a minute you'll hear more about the details of the capture part. The CO2 is captured and it's transported in one way, and this could be, of course, this could be within a facility. It could be very short if you're taking it to reprocess the CO2 in some way, but it could also be a very long distance if it's taken by ship to a storage site. Could be thousands of miles, and then you get to a point where you either have storage in a underground reservoir of some sort, or utilization. Then and here you see the sort of the difference between the C and the U at the very end of the BECCS part. And that to give you just a short overview, and then I'll hand over to Tero, who will talk a little bit about the specifics of CO2 capture in different sectors.
Okay, thank you, Ole, and welcome everybody from my behalf also. I will start with sustainable sources of biogenic CO2 and what are the main sources. And in lower right-hand corner, we can see the theoretical minimum work for separating CO2 from different sources, and of course the higher purity we have in CO2, less work and more easier process we have, and starting from high-end concentration, we have bioethanol fermentation, where we have very high purity CO2 and only practically drying and some purification depending on CO2 use may be needed. And currently, world's largest bioenergy CCS plants are all practically based on bioethanol production, and in top right corner there is a figure of this ADM BECCS plant where bioenergy production from corn processing facility CO2 is taken and stored. Coming to lower concentration, next comes gas digesters with about 40% of CO2 content. There is different options. This biogas can be upgraded by feeding hydrogen and producing more biogas, or then we can separate CO2 from biogas and either store or use it elsewhere. Then further down to flue gases, pulp mills are a big source of biogenic CO2. Current chemical pulp mills has some more than 350 megatons CO2 per year, and it is assumed to increase. Paper use and paper production may be decreasing, but other pulp-based products like replacing for plastic products are expected to increase, and in future the global potential of CO2 from pulp mills could be something like half gigatons per year. Waste to energy plants are one biogenic CO2 source which is likely to remain and important in this BECCS. Solid waste is typically more than 50% biogenic, in future even more, and although we try to recycle more materials and use materials more in different forms, there is more than 70% still landfilled of current wastes, and waste to energy plants are needed, and it is much better option to produce energy than landfill, and then we can avoid landfill gas emissions also. So we have different sources, and from different sources we have different technologies and different capture costs. There is quite large variation in estimation of capture costs, and as said, there is not so many large-scale CCS or bio CCS plants available, so clear, let's say, future cost estimates are difficult to give. But we have some idea, and this figure shows roughly around 2050 or a little bit earlier what could be the CO2 capture costs and capacity from different sources be. So these concentrated sources like bioethanol, biogas, they are quite limited in capacity. They are easy starting points, but not really solutions for climate change scale CO2 capture. Then next comes pulp and paper and waste to energy plants, which are can be considered quite good and sustainable options for biomass. So these are anyways wood streams that are utilized, and we are now just utilizing the carbon in higher concentration, so taking also the flue gas carbon, capturing it. And then this bioenergy crops, dedicated bioenergy crops, there is a very high variation of estimations what is really the sustainable capacity we have, and these land use change issues. At the same time, it is forests are important carbon sinks, and we need to be sure that we are not cutting those in energy crops. But anyway, we have a good sources, and we can handle part of the problem with BECCS, and it is required. Some part probably we need also this DAC, means direct air capture of CO2. So more expensive, but to have these capacities needed for overall negative emission targets required by 1.5 or even 2 Celsius degree targets, it seems that bioenergy is not only solution but important solution there. And going to technologies, I don't go in this brief presentation into details, but practically all technologies that are available for let's say traditional fossil fuel CCS can be applied for biomass CCS. There are some differences depending on biomass source. Usually we have higher moisture content, higher hydrogen content than in most of the fossil fuels, so it leads to quite large flue gas condensers. We have a very moist flue gases, and we need to condense flue gases to separate CO2, so we have very large flue gas flows to condense. This can be partly even good thing. We have a lot of low temperature heat available in flue gas condensing, and that can be partly utilized in, for example, in district heating or in CO2 capture, which requires also heat. In some of the technologies like oxyfuel and calcium looping technologies, we use calcium oxide, oxygen for separating CO2, and then in some processes like pulp mills are a good example of process where these all materials, calcium oxide or limestone, oxygen and carbon dioxide, are used also in this pulping process. So there is several integration possibilities which can make it easier and cheaper to capture CO2. Also, when we go to carbon capture and utilization, we combine CO2 with hydrogen, and hydrogen is produced usually by electrolysis, and then byproduct oxygen from water electrolysis can be utilized for CO2 capture as one example of integration to bioenergy CCU. So this was very briefly gone through main CO2 sources, biogenic, and then what are the main technologies and how it can be realized. And I will now give a talk to Christian, I guess was next to talk about transport part of the problem.
Thanks, Joe, and thanks to everyone for tuning in. Nice to see so much interest in our work. Yeah, I'm moving right along then. Having captured the CO2, the next stage is transporting it to where it'll be stored or utilized. And how to do so largely depend on the quantities being transported. When we're looking at onshore for small scale and pilot projects, this will largely be by tanker, rail or truck. And moving up to medium or large scale projects, pipeline is the most cost effective method. Pipelining of CO2 is a well-known and mature technology. It's been commercially used in the United States since the 1970s. When we move to offshore, it's a little less straightforward. in terms of it should be shipping or pipeline, and will often depend on some quite project-specific factors. For pipelines, some of these factors include the terrain through which the pipeline will cross, the diameter of the pipeline length. But generally speaking, pipelines are most suitable for short transport distances, large volumes, long project lifetimes, and relatively constant CO2 flows. A 2016 study in the Nordic context, for example, looked at transport costs with annual amounts of 5, 10, and 20 million tons. And with 5 million tons, it became more cost effective to ship when the distance exceeded roughly 730 kilometers. And we doubled this to 10 million. The analysis showed it was roughly 950 kilometers. And when we started looking at 20 million tons a year, it was first in excess of almost 1,200 kilometers where it became more cost effective to use shipping. Of course, there's also non-cost related aspects that should be looked at in terms of flexibility, reliability, environmental considerations. Flexibility could be the timing of the CO2 flows, if they're very seasonality dependent. Reliability could do with how the CO2 is to be used. For example, if it's being used in offshore enhanced oil recovery, then it might be very important that the delivery isn't interrupted by severe storms. And when we say environmental considerations there, we're talking about the greenhouse gas emissions associated with the transport, particularly with shipping, which would be directly related to if it's fossil fuel based or not. And the last stage we look at is the sequestration of the CO2. If we look at geological storage, one of the large options is deep saline formations. These saline aquifers are plentiful worldwide, both onshore and offshore. And essentially this involves pumping CO2 deep underground into a layer of porous rock. This porous rock traps the CO2 and combined with a cap rock of dense rock above sequesters the CO2 below ground. At depths below 800 meters, roughly, CO2 reaches what we call a supercritical state. In the sense it still behaves like a gas in diffusion terms, but has density properties of a liquid. So for example, at the surface, a ton of CO2 occupies roughly 550 cubic meters, but this can be reduced to 1 to 2 cubic meters at a kilometer below the surface. And another alternative is depleted oil and gas reservoirs. These are prime locations for injecting CO2, as the pore space that was once occupied by oil or gas can now be filled with CO2. And geologists are quite familiar with these sites. They've already proven that they can contain oil or gas for millions of years. Now, an alternative to simply sequestering it is utilizing or sequestering portions of it. And a very prominent example of utilization of CO2 on a large scale today is via enhanced oil recovery. This is essentially injecting CO2 into an oil well to increase the recovery rates. And at good sites, recovery rates can be increased by almost 50%. Now, it's important to note that some of the CO2 returns to the surface with the oil, while a portion of the injected CO2 is sequestered permanently. But today, oil companies generally have to pay to receive the CO2, so there's a very high incentive for them to capture the CO2 that comes up with the oil and re-inject it. So in this sense, we can say it's a relatively closed loop. Based on 2017 data, there was roughly 100 CO2 EOR projects globally, and they produce almost 500,000 barrels of oil per day. The vast majority of these being in North America, I think over 85%. Currently though, most of these projects, the CO2 they utilize, it comes from nearby natural sources. That is to say, it doesn't come from capturing at a power plant. But there are some exceptions. And for example, a few projects have illustrated the feasibility of utilizing captured CO2 from gasification or gas processing plants. And this gives us, brings us over to a potential opportunity going forward, and that's using bioenergy-based CO2 in EOR. If, for example, the CO2 that was utilized in CO2 EOR instead was captured from biomass power plant, then this would greatly reduce the CO2 footprint of additional oil produced. The extent of this reduction will depend on the amount of CO2 sequestered per barrel of oil, and these estimates vary significantly. One IEA source estimates that between 300 to 600 kilograms of CO2 is injected per barrel of oil produced. When we say this, though, one should also note again that because the oil companies are looking to maximize oil production per ton of CO2, there are potentials for increasing the amount of CO2 that's sequestered per barrel. For example, one could inject additional CO2 into nearby depleted oil or gas wells. But it's also important to point out that this idea isn't without its potential problems. Firstly, given that the CO2 content of oil itself, each barrel has about 450 kilograms of CO2, to which you have to add about another 100 kilograms of CO2 for processing. This brings about the question, should we be increasing oil production at all? On the other hand, some would argue that this low carbon could potentially replace some high carbon oil. So, and related to this, another issue is the question of how to share these CO2 reductions between actors. For example, if you look at the figure down the bottom right here, we have this biomass-based power plant that's in essence, if it was just sequestering the CO2, would be producing negative emissions, but now some of these emissions or many of these emissions are coming up again. So how do you appropriate these CO2 reductions between the biomass plant and the oil producer? Some of these aspects will be touched upon later in the project or in the presentation, sorry. But for now, I will turn it over to Daniela.
Thank you very much. I just also introduce myself. My name is Daniela Train, and I will now follow the utilization of biogenic CO2, the BECCS aspect along the value chain. Utilization of CO2 is possible and also already realized with fossil and biogenic CO2 sources, but we have heard that there are some advantages if we take biogenic sources, such as we have mature capture technologies, we can build on concentrated streams of CO2, and we can have additional revenues for the bioenergy plant operators when CO2 can be sold for CCS or CCU. Utilization of biogenic CO2 sources can be realized in different pathways. The physical pathway, direct use of CO2 in liquid or gaseous forms, such as beverages, greenhouse, CO2 fertilization, or enhanced oil and gas recovery, which is connected to storage and what we already heard from Christian. Material use of CO2 is typically a combination of CO2 with hydrogen to produce synthetic hydrocarbons, for example, platform chemicals and plastics, as a product from the transformation of the hydrocarbons. And the same approach is done if we go for energetic use. Here, the hydrocarbons which are produced are typically diesel jet fuels or also gaseous fuels like methane for grid injection. When the hydrogen is generated from green electricity, the hydrocarbon generation of the materials and energy is called power to X. Power to X consists of typically fluctuating renewable electricity source, wind and solar, which is separated or which drives electrolysis of water, where oxygen and hydrogen is separated. And in parallel, we have a CO2 source. We heard already a lot about possible sources here. And those two streams are combined in a power to gas or power to liquid reactor to produce power to liquids, power to gas, or even chemicals. There's for power to X already some pilot examples available. One pilot plant is the one here shown. It's in a world lab in Germany. The plant consists of 6 megawatt electricity input to 1,300 cubic meters per hour hydrogen production, CCU, and SNG. And you see the parts here. This is a combination of biogas plant with electrolysis. Here's the electricity supply and the electrolysis unit. On the other hand, here we have a classical biogas plant, and this biogas is on one hand, it's upgraded to biomethane, which is fed in here in the amine scrubber, and the byproduct is CO2. And this CO2 is together with the electricity, with the hydrogen from an electrolysis unit converted into methane in the methanation unit and also fed in. In some, we talk about 300 cubic meter per hour additional synthetic natural gas and annual amount of CO2 sequestered of 2,800 tons, and this equals about 220,000 beech trees. For economic feasibility, those units have to be in larger scale. So for BECCS, we can also think about pooling of different biogenic CO2 sources as an option. In sum, CO2 is an important technology for more resource efficiency. CO2 from renewable resources extends the resource base. I've shown you we can, let's say, have a longer value chain, but it is also a form of waste treatment that contributes to a circular economy and reduces waste streams. It can generate additional value and drive innovative business cases in new market segments. So far, we have to state that Power-to-X applications are often more expensive than other options, for example, bio-based fuels. And we also see additional limitations that we need large CO2 volume flows. This is a point which is a limitation for all kinds of BECCS and BECCS processes, which can be realized by biomass co-firing or by pooling from smaller scale sources. And it's important to understand that CCU has can contribute to CO2 reduction, but also under optimistic long-term assumption, this is a share of about up to 6% reduction of anthropogenic emissions. So it's interesting but limited. And with this, I would like to hand over to Ole. Ole, we don't hear you yet.
Thank you, Daniela. So to conclude here, I would just like to, I guess, say a few words about how public policy could be used in sort of taking BECCS further up the TRL ladder and sort of getting it to commercial stage. So obviously, there's a lot of issues that need to be cleared up here pertaining to like regulatory questions. For example, CO2 transport across boundaries is something that's been discussed a lot. Obviously, we also need to look at issues that sort of make sure that when you set up these approaches to capture and transport and store CO2, that you do that in a way that doesn't come into conflict with other sustainability ambitions or stakeholder concerns. Just to, in the final two slides here, so I'd just like to focus on two issues that are related to sort of economics of these supply chains. And first of all, you can see there's two main challenges there. One is about sort of innovation support and taking these technologies to full scale and maturity. And the second one is to make sure that there's actually a market for this service that you might say. The first one is basically innovation support. A lot of these technologies in terms of capture, I saw there was a question in the Q&A about TRL, and it varies between sectors. But there are very few of them that are actually at fully commercial scale that you'd have a proven business model, except for possibly the bioethanol case. But then take this, they might say, well, it's technologically mature, so it shouldn't be much of a challenge. But actually, this is where the key challenge comes in many cases, because to get to those higher levels of TRLs, you have to build oftentimes very large and very expensive commercial demonstration facilities, and that at the same time are sort of unproven technologically and commercially. So here's one specific field where public support will be needed to fill that gap and to sort of cross this sort of valley of death, as it's called, to take that final step to commercialization. So a technology is not proven, just because it functions in a lab. It has to be proven at scale and also in continuous operations and as part of a broader supply chain. So the whole thing. So this is one thing where public financing would be quite important. And then of course, you need to have once you have the thing operation, you sort of cover capex, but you also need to sort of find a way to generate revenue from this service of providing negative emissions. And actually, there had been quite a lot of activity in the last couple of years about setting up these sort of markets for trading negative emissions, trading sequestration of carbon. And there's also been some quite interesting statements from interestingly large tech companies like Microsoft and others who've sort of committed that they will voluntarily buy negative emissions to sort of make up for both their internal emissions, but also historical emissions in Microsoft's case. So this is very, very laudable, but I don't think it will be enough. There will be public policy measures that are needed to incentivize this, because you need to have something to reward you for setting up, doing these quite expensive projects, which really don't have much value otherwise. So there are a couple of different alternatives that have been discussed or planned or actually implemented. So one thing that comes to mind easily is to include it in emission trading schemes, for example, the one in the EU. The problem there is that the EU ETS at least doesn't really have a function to account for negative emissions. So that's something that might take quite some time to add, and given the sort of regulatory complications there, it's not something you can see in the near term. There are also been discussions about sort of following some of the examples that have been used in renewable energy. So you could either have a feed-in tariff, for example, or you could have a public procurement and a sort of reverse auction system where you would say, well, we're going to buy 2 million tons of negative emissions, and we'll give it to the lowest bidder who can do this in a scientifically proven way. This is actually something that's been proposed in a recent governmental investigation in Sweden, that there will actually be a procurement process. Exactly how that will set up, it's not clear yet, but it seems very serious. Also, tax credits in the US, they have something called the 45Q, which is a tax credit for capturing CO2. So it's regardless of fossil or biogenic. But interestingly, this can also be combined with another policy measure they have in California, the low carbon fuel standard. And if you combine these two, you can actually get to really high revenues for CO2. I'm not sure whether that's been actually implemented yet, but conceptually it seems like you could get to even, I think, around $200 per ton of revenue. So that's quite substantial. All right, so just closing up, a few key points moving forward in terms of discussion. I think one thing that came out of this is that there's really a need to close the sort of policy gap between fossil and biogenic CCS, because in several cases, as we heard Tero talk about, you can see that the capture costs are in many cases, or at least in some cases, lower for biogenic processes than for fossil, especially in bioethanol. But there's no real incentives there for biogenic CCS to be captured. That's something that needs to be addressed. And I think policymakers need to start looking into how to do this in practice and all within their sort of legal frameworks pretty soon. Then, of course, BECCS is an interesting thing because it obviously has a lot of benefits in terms of possibly driving technology of capture and also providing new products that in sort of recycling CO2. How to develop this for maximum mitigation benefits, I think that's very interesting. And also, especially, there's a need to basically start looking into the individual mitigation benefits of each individual case and have a sort of overview of how the carbon dioxide storage times vary and what effects that has on sort of mitigation potential. And one clear example here is Bioenergy, which Christian mentioned, that you can have use biogenic CO2 for enhanced oil recovery. And if you do that, there are ways you can do that which actually sort of results in you sequestering more carbon dioxide in the ground than what results from the oil that you produce, which essentially could be interpreted as you have like negative emission fossil fuels, which raise, I think, very interesting questions in terms of where you would handle that politically and also from a policy perspective. So on the one hand, you're saying, well, it's negative emissions. On the other hand, it's, well, you're also contributing to a fossil fuel lock-in or potentially basically subsidizing fossil fuel production. So I think those are some really interesting questions that we can look at moving forward. Just closing now, I can say we have a report around this that we just published today. It's available on the IEA Bioenergy, the Task 40 IEA Bioenergy website. And we will also, this is first step of a project that we'll be moving forward with in a couple of, in the coming year, with the case studies and some further looks at also the, hopefully on the looking at the sort of carbon accounting around BECCS. So I think that with that we wrap up, and thank you for your attention. Look forward to some questions.
Yeah, then it's my pleasure to introduce the Q&A session. So my name is Alena Hahn. I work for the German Biomass Research Center. And we have gotten more than 40 questions already, and they are still coming in. So I won't be able to ask all of them, but I try to synthesize at least some of them. Maybe going back to the beginning of the webinar, namely the CO2 capture step, there were many questions about this particular part of the webinar. So maybe to ask Tero first, you had this graphic about the estimated capture costs, and there were questions about what bioenergy crops stand for in this graphic.
Sorry, can you repeat what bioenergy crops?
In your graphic about estimated capture costs, you were there were mentions of bioenergy crops, and our listeners were wondering what you meant by bioenergy crops in that graphic about estimated capture costs.
Yeah, it's, let's say it's all else than in these other processes. There was also a question about why I didn't mention biomass power and CHP plants specifically. So this bioenergy crops is mainly bioenergy used for heating, power production, combined heat and power production. What is not in these other blocks and dedicated to this energy use. Maybe also to highlight that there was a question I noticed about this a little bit misleading scale of the figure. There is logarithmic scale, so the differences in prices are not so obvious as in reality, but it was maybe to put it in one figure, and this especially the direct air capture cost looks quite low in this, but it is in logarithmic scale. So partly to also don't want to give a detailed exact numbers, because there is no such exact numbers if we talk about capture cost in future, and there is a quite wide variance in estimations.
Yeah, thanks. You have even answered 3 of my questions, so that's
okay.
But
yeah.
maybe just checking in again on the estimates for cost, because there has been quite some debate in the Q&A sessions about the direct air capture costs, which were stated around 100 euros per ton for CO2 capture. Could you comment on this, where this figure comes from, or about the validity of this estimate?
It's actually closer to 200 euros per ton. I think there was this misunderstanding about the figure scale. So yeah, there is some wide variation in estimation. Maybe this close to 200 is lower end of estimations for 2050, but there can be justifications for having a technology development in different parts of this mainly energy consumption of sorbent materials for DAC.
Then maybe one more question for you before I move on to Christian, because you have just mentioned also the energy consumption. There was another question, if you can further state something about the energy requirements of those different carbon capture technologies.
Yes, well, let's say most major technology amine absorption energy consumption is roughly 3 to 4 megajoules per kilogram CO2, and maybe then this kind of developed sorbents and very tailored sorbents can lead to significantly lower costs, but those haven't been applied in large scale, and also if we go to very exotic sorbents, then the large scale applications may not be so feasible, but it is somewhere from 2 to 4 megajoules per kilogram, but I think the only energy consumption number is not important. It is also how it can be integrated and what is the quality of energy that is used for CO2 capture, whether we use low temperature heat or high quality electricity and so on. So it's difficult to give exact numbers for energy consumption.
Okay, then thanks for that. And moving to the next stop along the CCS chain, or moving to the storage part more of it. So Christian, there were also some questions about this, notably if you could give a rough estimate about the current geological storage availability, and also specifically storage areas that are close to existing CO2 point sources.
I think I'll take the first one first. In terms of these deep saline aquifers, my understanding is we're up in thousands of gigatons globally, but I must admit I don't have the exact figures in front of me, but that would be my off-the-cuff estimate. In terms of, sorry, your second question was large point sources close to
storage areas.
Yeah, again, it's also my understanding that these are fairly spread out, these aquifers. They're can be found many places. So I think in many cases they will be fairly close to large point sources. And I know there's been some work done with this, some mapping of potential clusters and both in terms of sources and in sequestration potentials. But I don't have that in front of me at the time, sorry.
Okay, and then further questions were related to the safety and the permanence of the storage of CO2 underground. Maybe you could give us some more insights about that.
Yeah, my understanding is, I mean, there hasn't been enormous amounts of work in this field yet, but there have been some testing and pilot projects and they've had fairly good results so far, or quite good results. But of course, there has to be some kind of long-term monitoring system put in place to ensure that if there are small leaks, that something's done to adequately rectify the situation.
Okay, that's great. And then maybe one last question also for you. Someone was wondering about bio-CO2 use for ERR purposes, and if this allows to really produce net negative oil and not just simply reduce the CO2 footprint of the oil produced.
Yeah, that one's very tricky because it all comes down to, over the long term, what's the total amount of net CO2 that's sequestered in your oil field, and what is the amount of net additional oil that's produced because of you've pumped this CO2 down into the ground. And the oil companies aren't, it's not readily available information as far as I can see. I've seen some estimates. I think I named one that it was between 300 to 600 kilos of CO2, and keeping in mind that it's about 550 kilos of CO2 in 1 barrel of oil. But these numbers really have to be taken with a grain of salt. There's a high degree of uncertainty with them, and it's definitely something we'd have to be looked into in greater detail before going ahead with long-term large projects where you're talking about certified green oil.
Okay, great. Then thanks for these further insights, Christian. Then I would move further down to the CCU part that we heard from Daniela. There was one question, if you could comment further on CCU being an option for fossil fuel replacement. And to what extent, because basically the question was that CCU obviously won't store the CO2 for an eternal period of time, but at least you will have this effect of fossil fuel replacement. And if you could give some more detail on that.
So thank you for this question. If we think about hydrocarbons using biogenic CO2, then this is exactly a fossil fuel or fossil resource replacement. And we can do this for fuels. And by producing power to liquids or power to gaseous fuels. There are also other options available, but I think these are the most important ones. And then, of course, the question of how long is the carbon, let's say, hauled into the value chain and emitted later on is an open question. And of course, here the carbon CO2 emission or release from the products is faster in fuels than in materials.
Okay, and speaking of power to gas, power to liquid, or power to X in general, there was one comment about it's not necessarily being the CO2 availability for these processes, but more the electricity that you would need low cost and low carbon. Could you share some more information on this part of the PTX process?
Yeah, I mean, the feasibility is influenced by 4 factors for power to X. One, of course, is the availability of a cheap biogenic CO2, and we've seen concentration of CO2 is driving the costs for the CO2 and capture. Second point is a question on cost for the renewable energy sources, providing the hydrogen, as you said. And here, if we talk about a green approach, then we talk about mainly about fluctuating renewable sources. And here we have very site-dependent cost structures. For example, if you talk about excess energy in wind parks, which cannot feed in the whole day, or if you talk about already well-financed wind parks, and you come up with low costs, talking about 2, 3, 4 cents per kilowatt hour, but of course it's also possible to have higher costs. So the second aspect is the cost for the fluctuating renewable energy sources. Third aspect is the scaling, and we need, especially for electrolysis, so far larger scale systems. And there the question is, how to bring the different streams, CO2 and fluctuating renewable sources together. And the fourth point is at least the integration in existing bioprocessing infrastructure. So if you just have already, for example, biorefineries where you can add additional processes, or do you really have to start new facilities? So it's very difficult to say what is a limiting factor. I think all these elements have to play together. And last but not least, under good conditions so far, it's difficult to come to feasible systems due to the limitations also Ola explained.
Thanks, Daniela. That's a perfect transition to my next question that would go to Ola indeed. One of the participants asked if you could explain a little bit more in detail what you mean by developing a policy mechanism for fossil and biogenic CO2, because it was mentioned that it does not really matter where the CO2 comes from as long as it's not in the atmosphere. So it doesn't really matter if, according to the person asking, whether it's actually fossil or biogenic or industrial CO2.
No, I guess that's exactly the point. But the fact that for example, if you had a in the European emissions trading scheme, for example, or emissions trading system, you have a price. I'm not exactly sure what it is now. At least before COVID, it was around 25 euros per ton of CO2. And if you had a CCS project, you would be able to claim those emissions for your storage. But if you had a biogenic CO2, as far as I have read up, you wouldn't be able to claim that stored CO2 as revenue, because the CO2 from your biogenic process would anyways be sort of assumed to be part of this sort of short carbon cycle, I guess, and then presumed to be counted as zero because it's offset against the land use emissions accounting. So I guess that's something there that needs to be addressed.
Okay, and also somehow related to this, I know that we haven't spoken in the webinar in detail about life cycle assessments and carbon accounting. Could you maybe shed a little bit more light on this aspect as well?
Yeah, so this is one thing that really intrigues me, and I think it's going to be really interesting, hopefully, if we were putting together a proposal to do a continuation of this project that will focus on that. So, and this, I think, is really very intricate, because obviously you have a lot of discussion about the carbon accounting around the biomass supply chain in itself. So even before you get into the stage of capturing the CO2. So the next question is then, if you take the carbon accounting for if you capture the CO2, put it in a product, how long is that product or that CO2 stored in that product? If you have some sort of plastic product, it might be decades. If it's the fuel, then it's just a matter of days or weeks or months, and something there in between. So an interesting thing will be how to of course, first of all, there's obviously a lot of life cycle assessments already being done about this, but then how to take all these analyses, put them into a policy measure or a policy framework that is specific enough to account for these differences, but also at the same time general enough so that you can actually put it in a legal framework. I think that's going to be quite interesting to see and look into those developments.
Yeah, then thanks for these final, or maybe like the almost final answer, because we are running out of time if we are looking at the clock right now. But there's one question that I find really interesting and that I would give to all of the panelists. This is namely the question of what could be the role of BECCS and BECCS in a post-coronavirus recovery. I don't know who wants to start.
I can start. No, I think there's plenty of there's obviously a lot of discussions about the sort of green recoveries and so on. I think there's a lot of potential to take the sort of long view here and look at, well, now this might be a good point to actually start looking into deploying negative emissions properly, and not just BECCS, of course. There are other technologies and land-based afforestation and so on, and reforest restoration and so on. So yeah, I think there's good opportunity for policymakers to take a step here.
If I just may add one sentence, we have seen with regard to the corona crisis that there can be larger, let's say, fluctuations in energy demand in the future, and let's say having facility available to produce more flexible fuels depending on the demand is one interesting aspect to be more robust and resilient for further crisis, and especially the combination of bioenergy carbon capture and power-to-X opportunities offers especially this sector coupling with a bigger flexibility.
Any further ideas by you, Tero or Christian, on this question? Otherwise, I would close this webinar with these last insights.
Yeah, I think I agree with the previous ones. Of course, it is important to target these. We have this Green Deal things and COVID funding to get economy going on, and in bioenergy CCS or utilization path, I think most important is to have this kind of large infrastructures and large demonstrations forward and funding for these, really to get from laboratory or small scale pilots to utility size projects would be certainly beneficial for technology development and also for this negative emission technologies.
Okay, Elena, I think we're coming to an end. So thank you, Elena, Daniela, Christian, Tero, and Ollie for today's presentation and for this very interesting webinar. And thank you all listeners for your great participation. The presentations and recording of the webinar will be available from tomorrow onwards on IEA Bioenergy website in the section Events Webinars. Next webinars organized by IEA Bioenergy will take place in September. So keep yourself updated by visiting IEA Bioenergy website for future information. And thank you, and have a nice afternoon and evening. Bye-bye.